So now we know how to make a flash ADC. So now we'll see what all can go wrong in this flash ADC. That's what we usually do. We want to do something, we come up with some circuit, see if the circuit works, and after it works we see what all can go wrong. So here we'll see what all can go wrong, and here the only main thing you have is a strong arm latch, because these things you guys know how to take care of it. So let's see what all can go wrong in a comparator. Okay. And we'll consider similar stuff we took for op-amp. Even for switch capacitor circuits we saw some non-idealities for op-amp. We'll do the same thing. We'll consider the effect of offset, what happens with the finite gain, again I'll write within quotes finite gain, and another non-ideality you can have is thermal noise. Okay. Now for op-amps dealing with thermal noise is much easier, but for comparators it is little bit more involved, so in the interest of time we'll not look at this. We'll look at only these two. So first let's see what is offset doing. So this is a comparator. So let us say the differential input is Vi. Ideally it is supposed to compare if this is greater than 0 or less than 0. So which means if I sketch the input output characteristic, how will this input output characteristic look like? If the input is less than 0, it is 0. If it is greater than 0, it is 1. Now if the comparator has offset, all that means is this characteristic can shift either to the left or right by any random amount. So let us say it is shifted to the right like this. So which means I will be comparing this with some offset voltage. So again this offset is a random phenomenon, which means if you make 1000 identical comparators and measure their offsets, they will all be random, but for a given comparator it will be constant. So this is what we have. Now let us see if this is even a problem, right? I mean, just because you encounter something unexpected doesn't necessarily mean it is going to be a real problem. Let's actually see if in our final system this will be an issue. And we are looking at flash ADC, so let's see what happens. So again, in a flash ADC you have bunch of comparators operating in parallel. Now let's say there is no offset in any of the comparators. In that case, if I sketch the input versus the output code, or the output versus the input, how will it look like? It's the step characteristic, remember. So we are supposed to get something like this. Fine. And what can you say about these code widths ideally? Ideally they should all be same, right? And remember these are the reference voltages with which we are comparing the input with, right? Okay. Now if the comparators have offset, and the bad thing about this is each comparator will have different offset because it's random. So how will this characteristic curve change? Yeah, I mean this reference voltage will keep shifting left or right depending on the comparator. So it's going to be completely random. You might get something like this. Okay. So what will happen because of this? You get DNL, INL, and that's essentially, if I apply a sinusoid, what will I see at the output? If we have DNL, INL, what is DNL, INL? Differential? A non-linear, which means if I feed in a sinusoid, at the output what all I will see? Yeah, in the spectrum, I will see the harmonics of the input sinusoid, right? So this straight away introduces non-linearity. So this is going to be a real problem. So we have to see what to do. Again, the thing to notice, if all the comparators had the same offset, this is not a problem. Because it's random, we have this issue. So let's see what we can do. So now let me take some number. Let us say this is some 1 volts, and let us say this offset, let us say it is some 5 millivolts. Okay. Now what it means, if ideally let us say there is no offset and my input is say 3 millivolts, what would have been my output? Output will be 1 volts. Now there is an offset of 5 millivolt and say my input is 3 millivolts, output will be, because 3 millivolts is going to lie somewhere here, this will still be detected as 0. So which means if there is offset I can have incorrect decisions. And now let us say the input voltage is some 300 millivolts. Do you think we'll have an issue? So do you think offset will be a problem for smaller inputs or for larger inputs? Smaller inputs, especially the voltages close to the offset will have issues. So if we have a larger input to start with, looks like offset might not be a real pain, right? So I should make sure that one solution is this. I should make sure that the input reaching my comparator is not really small, it should be really large. So what should I do? Simple thing is you try to amplify it and feed it to the comparator. Okay, so that is something we commonly do. So we try to put an amplifier before the comparator. Let's say it has a gain of A, and this is called as the preamplifier. So earlier, if the comparator had offset, we were doing this. The comparator was checking if Vi minus Vos is greater than 0. Now if this is Vi, what is the signal reaching the comparator? So the comparator will work on A times Vi and check if it is greater than 0. This I will rewrite like this. So which means what has happened to the effective offset now? Earlier I was having an offset of Vos. Now looks like it has become Vos by A, right? So the act of putting an amplifier up front has reduced the offset of this fellow by a factor of A. Now it turns out there is another added advantage with having an amplifier, and that helps us with the second non-ideality, which is finite DC gain. Okay. So by finite DC gain, what I mean is this. Remember that in our comparators we are going to have a regeneration, that e power plus t by tau phenomenon. So and the output is roughly the input times this, loosely, right? So let us say this regeneration is happening somewhere and we get here. Now the input becomes, do you think the time taken for comparison will be larger for larger inputs or for smaller inputs? The time taken for comparison, do you think it will be longer for smaller inputs or for larger inputs? Remember the output goes like this. If my Vi is also smaller, this will also be slower like this, right? Okay. So which means, let us say for really small inputs, it can so happen that at the end of my comparison phase, the comparator has not made a proper logic decision, right? It is neither close to VDD nor close to 0, lying somewhere in between. And what is this called in digital circuits? What? It's metastability. If a signal is not in any of the defined logic levels, we call it as metastable. And that is effectively what will happen if the, within quotes, the gain of the comparator is not good, right? So now basically the logic will depend on random noise in the circuit and how the succeeding digital logic is kind of detecting this. So this is an issue, and as you guys recognized, this is a issue for small inputs, not for larger inputs. So which means before I feed the input to the comparator, if I amplify the signal and feed it, this problem will obviously reduce. So this guy helps in two things. It reduces offset and also I will say reduces metastability, or better I'll say helps in metastability. Cool. But one thing is, there are a couple of minor points to note while making the preamplifier. Now let us say you are making this with strong arm latch, this comparator. Strong arm latch, do you think it is consuming static power or it doesn't consume static power? It doesn't consume static power. That's the thought process with which we came up with the circuit. Now if you go and put an amplifier, the traditional amplifiers that will be consuming static power, destroys the entire dynamic nature of the circuit. So in practice we don't try to have static amplifiers as preamplifiers. So we try to use what is called dynamic amplifiers, which consume power only during clock transition. That is number one.
To counter offset and to counter finite DC in a solution mostly use preamplifier.
Correct. This is one of the solutions. Okay. And this is commonly done. Now second thing is, remember we tried to introduce this amplifier A to help with offset, and this is reducing the offset of this fellow. But in that process, this guy should not have an offset, right? If this amplifier itself had an offset, nothing you can do. So you have to, let us say, reduce offset of the preamp. So two things we have to take care. So we'll just look at it and end today. Okay, so again, there are different ways of having a dynamic amplifier. I will just show one simple variant. In the interest of time, I will directly show the circuit. So the basic structure is this: you do something similar in strong arm latch. You have the input given to this. Again, as long as you are dealing with analog circuits, this structure will never leave you. It will keep haunting you forever. Okay. So you feed the inputs here as usual, and you clock it as before. And what we do is the following: you try to have a switch here made with PMOS. Something like this. Okay. I'll say 5A maybe, so that it's amplifier. The idea is very simple, same thing as we did in strong arm latch. So let us say this is, I don't know, yeah, V1, V2. So when phi A is 0, what happens? What's happening here in phi A is 0? This is completely off, PMOS is on. So again, remember there is always capacitance. So what will happen to the outputs? What will it set to? What will it reach finally? It will reach VDD. So if I write like this, phi A as 0, and if I plot both x and y, the output voltages, they will be at VDD. Same thing. So now the amplifier is going to be active in clock phase phi A. So in phi A, what can you say about the PMOS? Turned off. So I'll basically put a cross there, and this fellow is going to be on. So again, we are going to draw currents here. Let us say I1 and I2, and let's assume V1 is greater than V2. So which of the two currents will be larger? I1 is going to be larger. So these nodes were initially charged to VDD. Now we are starting to drop currents. What will happen? They will start to drop among x and y. Which will drop faster? X will drop faster, something like this. Now if I try to write expression for Vx of t, how will it look like? VDD minus
that current
I'm drawing a current I1 from this. Let's assume for a simplicity that V1 is constant, V2 is constant. Okay. So if V1 and V2 are constants, what can you say about these currents? They are also constants. So how will the voltage look like? I mean,
integral of I dt by c.
yeah, and I is constant, so that's going to be C into t. Fine. Similarly, the y of t will be what? Now if I define the output as Vx minus Vy, that's simply I1 minus I2 C times t. Now if I look at the total current I1, remember I'll have some bias voltage here on top of this. Okay. Now corresponding to the bias voltage, you will have some quiescent current, something, say some I0, and then a small signal V1 is applied. What will be the small signal current added?
V1 minus V.
GM times V1. Okay. This is shorter to ground. Okay. And what can you say about I2? So if you take the output difference, you will get basically GM times V1 minus V2 by C into T. This is V out. Okay. So now you see that the gain what you get here is this. And basically if I try to find V out by V1 minus V2, that's basically minus GM by C times T. So if you wait long enough, you can actually get a large gain, right? Basically you see that the difference between the outputs, they kind of keep increasing. So if you wait for sufficiently long time, you can get a gain.
But if you wait for sufficiently long time, then I1 will be a function of ADS. Any one of those currents will be a function of ADS.
But no, eventually see, if you keep doing this forever, what will happen to the voltages?
Keep on decreasing.
And then?
At one time they
You keep on decreasing and finally they will go to 0. That's completely right. So that is why, right, you should choose your component values accordingly. See, remember the point of this guy is to go and act like a preamplifier to my strong arm latch. So I'll make sure that till the strong arm is kind of responding, for the maximum input also the voltages don't drop to 0. Right? You choose your component values here accordingly, so that till the strong arm is kind of actually acting, I am somewhere in this region.
T should be small enough so that both the embedded and two are in separate.
Yeah, or you can put a large C, right? I mean, everything is in your control. You choose this accordingly. I'm not getting into details, but this can be easily done, and that's something commonly done. Is that okay? And one thing is, when are we drawing current from the supply VDD? Yeah, same thing as strong arm. Only while we are charging these capacitors to VDD is when we are drawing current. So if I actually draw the clock waveforms, this is phi A. So at what time instant exactly are we drawing current from the supply? Let's say this is the current IS I want. If I sketch IS, how will it look like? When the clock is active, are we drawing any current? Nothing. And when are we drawing any current? When this guy goes to 0 is when we are trying to charge this to VDD, and that instant we will be drawing an impulsive current like this. So again you see it's a truly dynamic circuit. So only when the clock is making a transition, particularly the falling edge is when we are drawing any current. So that way the first part is set, right? We are making sure when we are using a preamplifier here, this is kind of dynamic. So only one last thing. So let's see how we can reduce the offset of this guy. And the common way we deal with offset is in the following fashion. So if you actually look at the reason for offset, the offset is actually arising here because this is the basic structure, even for the strong arm latch or even for the preamplifier we saw. So we have something here, right? So for the preamp, let us say we have this. Ideally, if I give the same input V1, V1, you expect that both the outputs fall same way, right? If the inputs are same, the currents are supposed to be equal, the outputs are supposed to drop equally, and this is assuming that the transistor properties on the left and right are equal. In practice, there will be a lot of mismatch. It can be mismatch in the threshold voltages, dimensions, anything. So which means even if the inputs are equal, the currents in the two transistors will not be. So it can so happen one current is smaller than the other. So which means one can drop faster than the other and you will have offset. Okay. So the same will happen for the strong arm latch also. So one brute force way to reduce offset is to basically try to increase the size. So this you can do for the strong arm latch also. So I will just mark it to reduce offset. You increase the area of the device. Okay, that is one thing. But this is not something you might want to do so much, because increasing the area means the gate capacitance increases. Which means things are going to be slower. If you have larger capacitance, you have to spend more time in charging those capacitances. It's going to be slow. So this is something you can consider, but if not, common practice is to do this. See, because of mismatch, we have offset, and the effect of this mismatch is that even though I am applying the same input here, the currents in the two branches are unequal. If I can somehow counterbalance this imbalance, I am set, right? So what can be done is the following. Let me remove this. In addition to this main differential, the main amplifier transistor, you can have a bunch of transistors in parallel. All gates are connected, okay, and then you select an appropriate number of them to put in parallel to the main transistor. Same thing you do on the other side also. You do the same thing. You have a bunch of transistors on this side also. The gates are all connected. Okay. And then you choose how many of them I should connect in parallel and put in parallel with either of the branches. The idea is this, right? If I feed the same input to the gates, the currents in the two branches should be equal. Now because of mismatch, I am finding that current in, let us say, the left branch is smaller than the right side branch. I need to, which means what should I do to the current in this branch? I should increase it. I can increase it by pumping in more current. To pump in more current, I'll add some extra transistors here. The number of things that you put in parallel is something that you have to decide, and let us say that you can kind of figure out and add appropriate number of them in parallel. Then you will find that this approximately becomes equal to this. Then you are set. So typically, let us say the widths of this are W1, W1. You can choose a smaller width, some W0, and you can have it in a binary weighted fashion like this, so that you can have multiple combinations. And again, you have to, for each comparator, you have to go and find out how many transistors I should turn on the left side and right side, so that when I have equal inputs, the things are balanced.
Is this circuit kind of current mirror like we are doing?
This is not a current mirror, right?
Depending on the bits, we can draw respective current, like how.
Yeah, the point is, basically this is like balancing two things, right? Earlier times when you buy vegetables, you buy vegetables on one side, people used to put appropriate weights and try to balance it. Same thing. There is an imbalance here. So let us say you want 500 grams of aloo. Let's say it's slightly higher. What the shopkeeper will do, will take some 2-3 alus and try to make it equal. Same thing.
But we're doing it for each and every preamp.
Yeah, each and every preamp, and you can actually do this for the latch directly also. Yeah, for each and every preamp you have to do this, and this can be done on the run using simple digital logic, right? So this is often called calibration.
So you can have an equal number of transistors selected on the IR.
Yeah. Again, depends. Your goal is to balance the two sides, depending on the different.
One has to be much
Yes. This W1, yeah, I didn't mention probably. Yeah, W0 is usually much smaller than W1 because the offset is going to be small. The currents you need to add will also be small. And this notion of calibration is you'll see it's pretty common. You'll see all places in circuits. Okay, this is something you can. So bottom line, then you make a comparator to reduce its offset. You can always put a preamplifier. Okay, but you need to make sure that the preamplifier is calibrated so that its offset is reduced. Okay, or you can also do the following. You can actually do this calibration on the latch directly because the same principle. So you find that if let us say I do calibration only for the latch, I am okay for my application, you can go on and use it. If not, if you want to reduce it further, you put a preamplifier and calibrate it. And if you still want to reduce it, you again go and calibrate this guy also. Depends on the level of offset you want. And of course, when you put a preamplifier here, it also helps with metastability. That is an added advantage. So bottom line, to correct for offset, one brute force technique that you can adopt is try to increase the size of the transistors, right? And if you find that beyond some point you can't do it, you do calibration. You actually can try to add a preamplifier, but the preamplifier needs to be calibrated. If you want to reduce the offset further, even for the latch, you go and do the calibration. Again, it all depends on what level of accuracy you want. Okay, cool. So I'll just mention one last thing and then we'll stop 2 minutes. See, this is a nice idea. I just want to mention this. We know that if my comparator has an offset, instead of comparing Vi with 0, I am comparing Vi minus Vos with 0. Now remember, in our flash ADC, we are trying to do the following. We are trying to compare my input with a bunch of reference voltages. So now, can you think of some crazy way, some crazy idea based on the two equations? This is what I want, okay, in a flash ADC. But when I design a comparator, seems like this is what is happening. Can I do something based on this? If I can choose the offset voltage somehow equal to the reference voltage, then I don't even have to subtract the reference from my input. Basically, you intentionally have an offset in the comparator so that the offset is roughly equal to a reference voltage, so that can be used in a flash ADC. Okay, and for this, typically the inherent offset will not be enough, so you can go and introduce offset. Again, you can do something similar. You can have multiple things in parallel and then switch on appropriate things and intentionally go and introduce an offset. Or other way, another technique to introduce offset is this. Again, the idea is to change the currents. You can put a bunch of resistors at the source and connect appropriate number of them in parallel to change the currents. Because I'm sure you would have seen this by this time. If I have something like this is like a voltage controlled current source. The current to voltage factor depends on this resistor, right? So which means I can have different number of resistors on either sides, and let us say in a flash you want let us say 15 comparators. For each of the 15 comparators, I'll go and turn on appropriate number of them on either sides, so that the first comparator will have an offset equal to the first reference voltage, second comparator will have an offset equal to second reference voltage, and so on. If I do this, think about it, now I don't need to generate reference voltages, I don't need to do, all this business of subtracting reference in currents or voltage and all these things. I don't even have to do. So what I'll have to do is basically do this thing and then give my input to comparators, and that's enough, because the references are inbuilt in the offset and you can actually exploit it. And this is also sometimes done, and this is what I call as a classic example of selling bug as a feature, right? As they say, if I usually say this: if life throws lemons at you, what is the saying? Make a lemon rice and eat. Yeah, it's the same thing, right? I mean, you have something, you think it is not useful, but yeah, if you put your mind to it, you can actually make it useful. Yeah, so whenever some egg breaks, they say, don't worry, put an omelette and eat.